Well, hello everyone, and welcome to the webinars hosted by EDB. My name is Monica, and I am part of the marketing team here at Enterprise DB. I will be your host for today's webinar, an overview of reference architectures for Postgres. I am joined by Michael Wheeler today. He is a senior sales engineer here at EDB. Before we get started, I just want to go through a few housekeeping items. This presentation is being recorded. We will be sharing the recording along with the slides after the broadcast. The lines are currently muted. If you have any questions, please feel free to submit in the questions panel. Today's session is scheduled for 1 hour. We expect the presentation to last most of our time today, and we will allot any extra time for Q&A. If we do not have time to address all questions, we will follow up afterwards with any attendee whose question was not answered. And without any further ado, Michael, over to you.
Thank you very much. So today's topic is the reference architectures, and this is the agenda. Short introduction into EDB. Talk about what is a reference architecture and the properties that are involved or inform such architectures. A list of core architectures and some add-ons to that architecture, and of course a summary and the Q&A at the end. So without further ado, let's go. So EDB was founded in 2004. Today we have more than 500 employees and more than 5,000 customers. 25% of those are Fortune 500 companies. Company is headquartered in Bedford, Massachusetts, with offices spread around the globe. What we do is all about Postgres. We deliver support, services, and tools that enables customers to deploy Postgres into enterprise environments with such things as high availability and so on. We've been total have more than 25 years of Postgres focus. And today, with the acquisition of Second Quadrant, we are the largest Postgres-focused company in the world. So, reference architectures. In this presentation, what we call the reference architecture is kind of a building block. It is a way to build your entire application or your entire application architecture and understand each of those components in the architecture, and by doing so it's easier to understand the entire architecture. The ones that are available on GitHub, which there will be a link to later on, are ones that have been tried and tested and are easy to understand, easy to try out, and can be used as the foundation for your application architecture and your database architecture. So let's talk about the properties of architectures, database architectures in general. And there are 4 of them. The first one is recovery time objective, which the short version of what recovery time objective is how long does it take you from your server, your database server, primary database server has failed until you are up and running again. That is what RTO actually is. And with that, you also have to be aware that if the server fails, the node that the database is running on fails, and all you need to do is restart it, then a failure is easy to recover from. But if you need to go back to a database backup or even an operating system backup, then it takes longer. And so that is the metric that you need to take into account here. Recovery point objective is the second property. In short, this is a measure of acceptable data loss. The way that this means that if you have committed transactions and your database fails, will you be able to recover those committed transactions, the transactions that happened in the past couple of seconds or maybe even hours? Are those available once you have recovered your database? If you have to resort to a backup, revert to a backup and restore from there, then your transactions, the newest transactions may not be recoverable, and so you've essentially lost those transactions. This is measured in minutes or even hours or even days. If you have a situation where your backup is 2 days old and you cannot recover, then you have lost 2 days worth of transactions. All of these properties are in themselves targets, so they inform your choices on architecture. So if you cannot accept, for instance, a few hours of data loss, then you need to build an architecture that insulates you from that data loss. The next one is geographic redundancy objective. Here we're talking about being able to survive a complete loss of, for instance, a data center. If your entire architecture and your databases, your failovers, and whatever else we're going to get into is situated in one data center, and that data center suffers a complete loss of power or even flooding or something like that, then you've lost your data center, you've lost your databases. Will you be able to conduct business afterwards? Your backups may be somewhere else, but you have no hardware to run them on. So what do you do now? So this is what geographic redundancy is all about. And the last one, and the most well-known one, is the target availability. This is where we talk about number of nines, so 99% uptime, 99.99% uptime, and so on. The degree in which a system is available, the amount of time where the system has been available measured across a month, a quarter, a year. And in this case, in the top right corner here, we have some numbers for availability seen across a year. So with 99%, it's you can suffer, you are allowed to be unavailable for 3 days and 15 hours, as opposed to with 6 nines at the bottom, where within a year you don't meet your required uptime if you have more than 31 seconds of downtime during that year. Now, again, a target is not a guarantee, and it is affected, and you need to take into account all the factors and dependencies that your database has, and that would be the operating system, the hardware that the server is running on, the network connecting you to your clients, the environment, things like cooling and power, but also things like upgrades and maintenance windows during the year. Usually in an SLA, they are not included in such a thing, so that if you need to do an upgrade of your database, that counts against your SLA and your uptime. So on to the core architectures: single node, multi-node, and multi-node with respectively asynchronous and synchronous replication. So a single node is this most basic deployment you can do of a database. You're running one server, just one server, and we do see some organizations running this on very not critical databases in production, but usually just deploying a single server is something that you do for development and testing purposes. In those cases, the database will usually have a script that resets it to a known state with test data inside it. And so loss of the database, loss of the server running, you can just set up another server and reset the database on there, and you're off again with your development or your testing. So, and as already stated, this is not recommended for production. You are vulnerable. Your recovery time and recovery point objectives are dependent on the database size and on your backup strategy. There is no redundancy geographic-wise. Target availability, again, depends very much on the environment that the database is running in, but usually you'll see something like 99.9% on just a single server. And it looks like this, right? One database server with clients connecting directly to the database server. You may have directly attached volumes, or you have volumes attached in some other way here, and you may have it separated into wall volumes and data volumes. It depends on the load on the server. So very simple deployment. Multi-node asynchronous with asynchronous replication. In this case, you have one primary server and you have a number of standby servers. Traditionally, these servers are set up as hot standbys, which means that they allow read-only connections into the database. This is very suitable for production environments. It has high availability. You can use the hot standbys as read scale-outs. It is write performant, but you run a risk because using asynchronous replication, the functionality goes something like this. The application inserts data into the database and commits. Now that once the application commits, the transaction is written to the WAL files, then the commit returns. From there, asynchronously, the transaction is replicated to a standby server that then applies the changes performed on its own storage, and now you have a replication. But it is asynchronous. So what could happen is that once the application commits and the transaction is written to the WAL file, before the transaction is replicated to the standby, the server crashes. From the application's point of view, the commit has returned, so this is committed data. But that data is essentially lost if you're not able to restore it afterwards. And so you do have a risk of losing data along the way during a failover. Recovery time objective in this case is somewhere around 60 seconds or less than 60 seconds. It's possible to set this very aggressively. I have seen very low failover times on some servers. The lower you set this, the more you run a risk of actually failing over, even though there's nothing wrong. This typically happens if the network has there's a congestion in the network or something that makes it so that the agents monitoring the databases are unable to connect to the database, and so they think that the primary server is down and then perform a failover, but the primary database was actually fine, but the network was the problem, and so you have that risk. Since the failover in itself is not that big of a problem, the problem here is that you're creating more work for yourself, right? Because now you need to restore your primary database. So that's recovery time. Recovery point objective is, yes, you as already discussed, you may lose some transactions along the way because of this situation that I've already described. Geographic redundancy is dependent on where you put your standby servers. And again, the distance between the servers, just from a network perspective, also informs your recovery point objective, because the further they are from each other, the longer the lag, or the bigger the lag will be between and the transaction being performed and the transaction being replicated on the standby. Target availability, 4 nines is guaranteed in using our tools. 5 nines is possible if you tune the failover. Again, you run the risk of creating work for yourself by doing this, but if you need 5 nines, then it is possible to do. And it looks something like this. In this case, we have a primary database up here in blue, 2 standbys, and the primary database is sending its transactions to the standbys with these blue lines using asynchronous replication. You have a number of clients, all read-write connections go to the primary server, whereas the read-only connections can go to the standby servers. So with synchronous replication, the architecture looks very much the same. It's a setting in Postgres that differs between those two, or actually several settings in the way that the databases are set up. So the only difference here is that by using synchronous replication, you're trying to insulate yourself from data loss. And it looks very much like this. With synchronous replication here, we again have a primary database server, and synchronous replication is happening to this standby server, and asynchronous replication is happening to this one. This is where the synchronous standby server's ability to apply the changes quickly becomes critical. Also for the primary database to the time it takes for the primary database to send or to stream the transactions to the synchronous standby becomes critical. So network becomes a critical factor here. Effectively, what happens is that when the application commits, data is written to the WAL files and streamed to the synchronous standby server. But the commit is not returning to the application until it has been applied and on the synchronous database server, and a signal has been sent back to the primary database that all is well. Then the commit returns. So you have reduced your risk of losing data to, well, effectively zero, close to zero, but it also means that your commits now take a longer time to complete. And so that's why the synchronous standby and its response time becomes very critical, because you're effectively waiting for 2 database servers to apply your data or your transaction before the commit returns. Again, in this case, all read and write goes to the primary database server. And again, you can use the standbys for taking the load from read-only transactions. Again, here, running very large read-only transactions on the synchronous standby will of course, slow it down. And so your primary database and its commits will suffer because of that. So there are a lot of things to take into account here. I have some extra architectures at the end of this webinar where you can sort of get away from this problem with read-only transactions. So connection pooling and load balancing, and why is that necessary? Well, the idea behind this is to limit the number of connections to Postgres. One of the things where Postgres differs from another very large and well-known database brand is that every connection to Postgres is an operating system process, whereas in some other cases it is a thread. And so you can say that connection pooling is built into the database. It is not built into Postgres. With a couple of hundred connections, this is not a problem, but 50,000, 100,000 connections, you begin to have a huge problem on the database, because every single one of those connections is a process in itself, which means that the server that the database is running on needs to manage those connections, or not manage, needs to manage the processes. And so there will be a huge load based on that. That's where connection pooling comes in. You now have a stable number of connections to the database, and the connection pool is leasing out those connections to applications as they connect. The reason why that works is because of the usual way that an application uses a database is it reads some data, then there's a pause while the user reads and decides what to do with that data, and then there's an update and a commit. And so for the reading, for instance, there is no need for, while you wait after the read, there is no need for a connection to the database, so that can be reused by someone else. PG Bouncer is a very simple and very effective connection pool. It does just that one thing. It's a connection pool. And it can separate, or you can set it up in such a way that the connection can be a read-write or a read-only connection. And in order for you to do that is that the application needs to know how to connect with a read-only or read-write connection. And that way you can separate and do load balancing, round robin, and so on your read connections. PG Bouncer is installable on Windows and it's installable on Linux. And it looks like this. In this case, we have a single PG Bouncer instance, and we have set up a read-only connection down here and read-write connections to this one. And the clients connect to the PG Bouncer instance and then lease a connection from there. In this case, of course, you have a weak chain because you only have one PG Bouncer instance. So if that server fails, then you have nothing to connect to the database. So what we usually do is we set it up like this, where you have PG Bouncer running on your database servers with connections, again, set up as read-write to the master database. And again, here from this one, read-write to this master database, and read-only can run on essentially both databases in this case. So that's PG Bouncer, very effective, very simple little program. PG Pool has a lot of more features, but it also comes with added complexity. It is a connection pool, but it can do so much more than just quote unquote be a connection pool. it is able to separate read-only transactions and read-write transactions automatically. Again, there is a risk here because pgpool doesn't really know if you're doing a select my function, for instance. It doesn't really know whether or not that is actually just a read or it is a read-write, because it doesn't know what the function is doing. So there may be some side effects, and so it will have to consider that as a read-write transaction. So you need to test how this functions with the database. So it's very dependent on how your application communicates with the database actually, and what you're using in your statements to the database itself. Also, inspecting every single statement as they come into pgpool, of course, means that pgpool is spending time passing the statement. And so that is, of course, a performance hit right there. Small one, but it is a performance hit. And it looks like this, very much like in the case with pgbouncer, and for the same reasons, having just one pool, as in this case, you run the risk of losing that server. So setting it up in this way enables you to spread the load, and you can also run dedicated, as in this case, dedicated pgpool nodes, but have more of them. So you can scale out in that sense. More architectures, this time for management, for enterprise manager, and for backup. So enterprise manager is a tool developed by EDB. It is based on pgadmin. So all the features that are available in pgadmin are also available in PEM. But what PEM adds are all the features that DBAs need to monitor hundreds of databases instead of just one. It has built-in dashboards. You can do capacity management inside. It has weight state performance analysis. This requires advanced server because it's an advanced server that actually delivers this functionality. It has SQL profiling inside it. Postgres itself has long-running transactions being logged to the log file, and sort of making you aware that you have a statement here that's running for 15 minutes. But in many cases, the statement that's running for 15 minutes is just a report, and it's only being run once a year, so it doesn't really affect your performance. What does affect your performance is one of the small transactions being run, but it's being run 5 million times during a day. And so that's the one that's actually impacting your performance more than anything else. So you want to be able to find these, and SQL profiling is the tool that allows you to do that. It also has wizards for tuning, logging, and audit. And most importantly, it implements what we call probes, which are statements performing and building metrics from the database that is being monitored. Things like table space size and CPU load, tons and tons and tons of others. I think we're past 200 different metrics now, just built into PEM. You can add your own metrics to that, and for all these metrics, you can set up limits in such a way that you will get an alert or a warning if a metric has a certain value, or is below a certain value, or higher than a certain value, and so on. So, for instance, an alert saying that this database server is suffering from high CPU load at the moment. If it's not supposed to do that, then it's a nice thing for the DBA to get an alert saying that this is happening, because then we can look at why this is happening. So all this can be set up, and you can get these alerts as mails, as SMTP, as SNMP, as traps for things like SMS. And in later versions of PEM, you will also be able to use a webhook to do this and send these notifications. So for instance, you can integrate Enterprise Manager with Slack and have a Slack channel that contains all your notifications. You can also integrate into other monitoring tools. Yes. It looks like this. In this case, we have a number of database servers. On each of these servers, there is what's called a PEM agent running. The PEM agent is the one responsible for running all the probes, gathering the metrics, and sending that information to the PEM server. These two are monitored in that way with the PEM agent running directly on the database server. This one, designated as a remote monitored, does not have a PEM agent. So in this case, it's the PEM server that is gathering the metrics. The PEM server will then gather a limited number of metrics, and you will have less functionality available to you. For instance, you will not be able to run batch jobs directly from PEM on the database server, which you will have available here, but not on a remote monitored server. So all the metrics are sent into the PEM server, and then the PEM server is the one analyzing the metrics and setting up notifications based on the alert profiles that have been configured for a specific server or for all the servers. PEM server itself is quote unquote just a web server. So all connections from clients will be HTTPS. So backup and recovery. Regardless of how you set up your high availability, you will need a recovery, a backup and recovery. If for nothing else, then when you need a failover, when you do a failover, you need to be able to restore your database on the failed primary database. BART allows you to do backups in full backups and incremental backups in parallel. It also manages your backups and the WAL files needed for restore. It looks like this. So it's usually it's a server. You set up BART as a server, dedicated server with BART, and then you have BART connect to the databases with libpq, the Postgres protocol, and with a secure shell. Also, the database servers themselves are copying the WAL files to the storage that BART has set up. And in this case, and this is optional, of course, is to have a SAN that stores all the data. It's usually a good idea to have a lot of storage, but also fast storage, so that your backups can finish as quickly as possible. And in this case, also optional, a backup to tape of the backups themselves. In the GitHub repository, the two architectures that I'm going to discuss now are not available, and I think it's important to mention them, but they are not as simple as the other architectures that have been discussed now. But one of those is unidirectional logical replication. So instead of using wall streaming and archive commands for your standby databases, and you want to offload your for instance, a reporting server or some other way or some other disaster recovery site or something like that. You want to completely offload that. What you can do is you can set up this kind of logical replication where you can replicate one table or even a subset of a table or an entire database for that matter. You set this up by table by table. And instead of this being wall streaming with log changes in specific files and so on, this is not the communication. In this case, the communication is based on tables and records, usually with a primary key. And that's why it's called logical replication. So you replicate the changes. And again, this is asynchronous. So you have eventual consistency. So data coming from, for instance, this server, if we consider this as the master server or the primary server, then changes are being applied here and then replicated to the other servers here. Asynchronously, so using these as read immediately after an insert being committed on the primary database. The row may not be available yet on the server over here. And there is, in this case, with logical replication, there is actually no way to get around that. You need streaming replication to do that, and synchronous replication. So this tool can connect to Oracle databases. It can connect to MS SQL Server. It can connect to Postgres. So you can actually, and we do this quite a lot, set this up as a way to replicate data from, for instance, an Oracle database to Postgres. And so now you have a copy of your Oracle data on Postgres, and you can use this to set up test environments. You can use this to set up development environments, or you can use this as a reporting server. So you replicate this data from wherever it is operational into Postgres, and now you can use that as the source for all your reports. You can also use this for disaster recovery or different kind of disaster recovery. If you're in this case, if everything goes wrong, you actually only need one or two tables or this schema. Then you can set up replication of this using replication server and have that replicate to an entirely different continent asynchronously. And then, yes, you run the risk of losing some data, but it's better than having no data at all. And then the last one here is multi-node bidirectional logical replication, also known as multi-master. Again, here we have several primary databases sharing data and replicating data between them. Replication server allows this, and we're able to do this, but there are risks involved in this. Mainly collisions between updates. So an update is happening here as well as here at the same time. So who gets the update? Which one of them is right? Another thing that you need to be aware of is that you cannot treat this as you would a normal relational database with ACID compliance, so immediate consistency. You are in a situation where you have eventual consistency because a commit here needs to be replicated over here, and it may not, it's not happening instantly. But it is possible to do this, and on Postgres, if you only connect to Postgres databases, then this is log-based, so you don't need triggers on the tables. Whereas with Oracle and MS SQL, you will need to implement triggers, or actually the replication server itself is gonna implement the triggers on the tables. So I've actually been a bit faster than I should have been, so we have plenty of time for questions.
Okay, thank you very much, Michael. So we have one question, which is asking if you could please mention whitelist or blacklist functions.
I'm not sure what is meant by that.
Okay, let's see what else we have. Another question. By default, streaming replication with replication slots in Postgres 12 is async. Could it be changed to synchronous?
Yes, I believe it can. New functionality in failover manager allows for replication slots to be used as well. So yes, I believe that's possible.
Okay. So clarification about the first question we asked. So PG pool can whitelist, blacklist functions. So select my function is not sent to read-only host. Does that make sense?
Yes, it does. And thank you for clarifying that. Yes, you can do that. But it also means that you need to define all the functions that are in your whitelist or your blacklist, of course. And with that, you can do it. But it is, as I mentioned, you need to test what happens in your application. You need to be very aware of what happens in your application in order to use this kind of setup with PG pool, automatically distributing the read and write transactions.
Okay, thank you very much for that. We have another question.
Yes.
So PEM and BART, how to avoid being a single point of failure in your design?
Yes. In this case, where we're showing PEM, let's see, where is it? Here. Yes, you have a single point of failure in the sense that if your PEM server is down, you won't be able to monitor your databases. And so in that case, your the PEM server itself has several components, agents being of course one of them, running on your database servers, but it also has itself a database server underneath the website that it uses. And so that server, of course, once PEM becomes a critical component in your architecture, needs to be treated just like any other database. So it needs to be set up with high availability, failover, and so on. Because otherwise, you lose your ability to monitor and your database, you lose your ability to get alerts on your databases. And of course, the web server itself is a lot easier to set up with high availability. You can easily set up several nodes and use them and to connect to the same set or same failover cluster of databases. Does that make sense?
Okay, thank you for your answer. Another question, can you describe some differences between physical and logical replication?
Yes. Physical replication talks about, or the communication there is about this, this block in this file at this address has changed to this content instead of the content it had before. This physical replication, Whereas logical replication is this row in this table has changed to these values in the columns instead of these columns. So it's a very different way of looking at change capture in the database itself. Physical replication is streaming replication comes from the WAL file, so the transaction log generated by Postgres itself from the database itself. Whereas logical replication comes from either triggers in the case of Oracle or MS SQL. So you capture the changes with insert, update, delete triggers, just like you would in the application itself. Or in the case of Postgres, you can actually read the log files themselves and pick up the same information, but then of course it's the logical agent interpreting the physical changes to become row changes or logical changes instead.
Okay, great. Next question, is BART server a single point of failure?
Yes and no. BART is a tool, it's not a server that's continuously running. So the main thing with a BART server is the storage. The storage needs to be treated very carefully because these are your backups. But running BART itself, you can run BART on a dedicated server, and this is usually a good idea, but you can easily have several servers where you can run BART that connects to the same storage. All you have to do is be careful not to run a backup on all of them at the same time for the same database, because that's going to be a problem. So yes and no, it can be a single point of failure in that sense, but BART is quote unquote just a tool, so it can be installed in several places.
Okay, brilliant. Our next question, is there a PG Pool Windows installation? If yes, is there some known issue?
Ooh, I can't remember whether PG Pool is available. There is on our website. There is a in the products tab. There is a list of all products and their availability, the versions, and where they are installed and supported, where they can be installed and supported. And I don't remember whether PG Pool is installable on Windows. I'm sorry.
Okay.
Is there a second part of that question, or did I forget something there?
No, let me go to the next question. So can you please go over the remote monitored server with reference to the PAM server?
Yes. It is we just happen to be on the right page. On these servers, you have a small process running, which is known as a BART agent. The BART agent receives the metrics or the probes, as we call them, basically just defined as SQL or a script running something and returning a value or two values or something like that. So an example of a probe could be current CPU load or table space size, right? So returns the table space size would return a list of table spaces and their sizes. And CPU load, of course, would return one number. So on database servers that are not remote monitored, there is an agent running here, and that one would be responsible for, I lost my cursor, but there it is. will be responsible for gathering the metrics and updating the PEM server, database with the information. In remote monitored case, there is no agent running. So the PEM server is gathering some of the metrics, the ones that are available, which will be the ones, since it has a connection to the database itself, it will be able to connect to that and gather metrics on the database server itself. So things like table spaces and tables and last auto vacuuming, things like that will be available, whereas all the all of the operating system based metrics are not available on a remote monitored server. So you cannot monitor CPU load or file sizes and things like that.
Okay, Michael, we have one question regarding one of your slides. I think this is a clarification that this person is asking about. So logical replication is not supported. There was a sentence of not a reference architecture in the slide.
Yes, these two. The reason why I'm writing not a reference architecture is because of this slide, which has a link, and of course this will be sent to you so that this link will be available, which is the reference architectures, and you should be able to see my browser now. So this is a link to the Enterprise DB GitHub repository that contains most of these, or actually all of these reference architectures and some text on them and some descriptions, and also the diagrams. But the two that I set as not reference architecture are not available in that. We plan to expand that, but that will not happen overnight. But I wanted to bring these into the presentation because I think that it's important to know that these types of architectures are also possible. So this is not a warning saying this will never work or so on. It's a warning saying this is not available in the link that is provided to you. That is all.
Oh, perfect. Thanks for clarifying that. Next question. In an architecture with 3 nodes, if the primary node goes down, is there an election between the read-only nodes to become primary, or is that statically defined?
Yes and no. There is an election. You can define a list of standby nodes that are supposed to be part of the failover selection, and the order in which they are listed is a kind of priority. So it will consider the first one in the list first, but it will choose based on which standby is up to date or is closest to up to date. So the one that lags the least behind and has the most data, because as discussed during the architecture of asynchronous replication, you will incur, or you do risk incurring a data loss when the failover happens. So you want the one that is that contains most of the data that you have that is on the primary database. The agents, by the way, in failover manager are connecting to each other using JGroups. So they are in constant communication with each other and aware of each other. So in a cluster status, you'll be able to see whether or not the database is up on another server, and you will also be able to see whether or not the agent is actually up itself. So you can also be in a situation where the agent has failed. That will be, of course, just require a restart because it's a fairly small program. Usually they don't go down.
That's great. Thank you very much. Our next question. when BART server is unavailable, backups stop executing?
No, well, backups are executed either manually or using cron. So you can set them up to execute automatically, or they are initiated from PEM. From this, PEM has an integration. Enterprise Manager has an integration with BART, so you can start a backup server or a backup of the database from PEM itself, because it integrates into the backup into the BART server. So yes, in that sense, if you have backups running on and executing on a specific on the BART server, they are of course connecting to a database, and if the database goes down or the BART server itself goes down in the middle of a backup, then your backups will stop executing. That's, of course, that happens.
Okay, the next question. Is the Postgres EDB asynchronous commit on primary server safe to use together with async physical replication? I mean, if some transactions get replicated to standby but primary server crashes before WAL fully synced to local disk, can replication recover automatically, or full database resync transfer to standby has to be done?
If you have synchronous replication set up between your primary server and one or more synchronous standbys, then your commits are safe, right? Because the commit does not return until the data has been applied to the synchronous standbys. So and as shown in this picture, you can easily mix and match between synchronous replication and asynchronous replication. Typically, synchronous replication will be set up where you have a fast application of the transactions, and so you need the synchronous standbys will be closer, geographically closer to the primary database than the asynchronous database server will be, because any kind of lag in your network and your commit speed suffers from this, and so your application is the delay is noticeable. Does that answer the question?
Well, I hope it does.
If not, just ask again.
Okay. So another question, and I think this is the last one we can answer due to our time allocated for this session. So from my knowledge, hot standby is identical to primary system. Is it also same to master server?
Hot standby is a server that is in continuous recovery and allows read-only transactions into the database. So you can use this to do quick selects or to run a report or something like that. If you have synchronous replication set up to that standby, then yes, it will be identical to the committed state of the primary database server. If it is asynchronous, then there will be a lag between them. So a transaction that has just committed on the primary database is not yet available on the asynchronous server.
Okay, perfect. So Michael, we have 3 more questions. Do you think we can answer them right now?
Yeah,
Do we have the time to do this? So
Yeah.
let's go with the next one. If I got you correctly, the DB servers send data to the PEM server and the PEM server gets metrics from the remote monitored server. Are these metrics gathered from the remote monitored server used as a reference, or what is the purpose of that?
Let's see. Here we are again. Could you please repeat that? I'm sorry.
Yeah, of course.
Difficult to understand.
If I get you correctly, the DB servers send data to the PEM server and PEM server gets metrics from the remote monitored server. Are these metrics gathered from the remote monitored server used as a reference, or what is the purpose of that?
Well, the purpose is that in some cases you don't want to have a PEM agent running. Usually it's a good idea, but there is the option of running as a remote server or remote monitored. The difference here is that in the case where we have, oops, sorry, I lost my microphone. In this case where we have non-remote monitored, there is an agent running on the database server. And that agent is responsible for gathering the metrics and sending it to the PEM server. So it's not the database itself, it is a part of the PEM architecture that is performing this task. In the case of a remote monitored server, the PEM server itself is gathering some of the metrics, but not all of them. The idea is that it could be that you're not allowed to run a separate process on this server down here, the remote monitored, but you are allowed to log into the server and monitor it. And in that case, you can use remote monitored. It is a limited functionality, so the best thing, of course, would be to have an agent running and have the full functionality of PEM available.
Okay, brilliant. Next question. Is it possible to set 2 PEM servers to reduce the risk of losing connection between clients and DB servers?
I would set a failover. So I would, first of all, I would split the PEM server or the PEM server architecture into the web server itself and the database. This is where our professional services come in, because then you need to be able to also not replicate functionality between the two web servers, because now every time there is an alert, you might get 2 of them, because you now have 2 servers performing the same tasks, and you want to avoid that. But you want to also just maybe be able to failover from one to the other. If the web server running your PEM interface fails, then you can do a failover to another server that also has the web interface installed. The databases themselves, you would set up in normal high availability, so with synchronous or asynchronous replication and so on that we've already discussed.
Okay, thanks a lot. And our last question. EDB Postgres replication server is based on logical or streaming replication?
EDB replication server is based on logical. The only part of that functionality that has anything to do with streaming replication is that on Postgres, it reads the transaction logs, so the WAL files, instead of applying triggers to the tables that it needs to replicate data from. On other brands, such as Oracle, MS SQL, this happens with triggers instead. So you have shadow tables with the changes to the tables or to the rows. On Postgres, it infers that from the WAL files, but it is not part of any streaming or physical replication whatsoever.
Okay, so this takes us to the end of today's session. So thank you, Michael, very much for this insightful session, and thanks everyone for joining us for this webinar. We will be sharing this recording along with the slides with you as soon as possible. I hope you have a great rest of your day. Thanks for joining again. Bye-bye.
Bye-bye. Thank you.